Today, we get to delve into stats a little bit. We start with definitions for two measures of central tendency, mean and median. Measures of central tendency are typically numbers given to best represent a sample. It's really common for us to use the mean or average to describe sample. We just add up all the values and divide by the number of values that we had. Notice there are two variables indicated here, mu, which is the upside down H-like letter, which indicates a population mean, and x bar indicates a sample mean. So the mu is only used if you know all the data. X bar is typically what we use because we don't. Mean works great for normally distributed data. However, the mean, while often a fair representation of data, is not always the best when data isn't normally distributed. For example, in my neighborhood, there are probably 400 homes that range from $50,000 up to $450,000, with an average of around $230,000. We also have Longwood Drive, where maybe 50 homes average $1.5 million. This picture isn't actually of any of the Longwood Drive homes. None of them were listed on Zillow when I started recording this. The average for the whole neighborhood might be close to $390,000, but nearly all of the houses are significantly less than that, while the median remains close to $250,000. The median gives us a better picture of what a typical house in the neighborhood might look like this one across the street from Professor Baker's house. Median really is resilient to outliers in a way that mean is not. We often use measures of central tendency to gauge the accuracy of our measurements. We also need to indicate the precision of our data, which we do with measures of spread. I've already told you that standard deviation is often our standard metric of precision. Standard deviation is calculated in two ways, depending, again, if you're measuring an entire population, so you have all the data, or if you're only sampling it. Again, we're usually sampling it, and so we'll use the S, the second of these values. If you are measuring the entire population, we use the sigma calculation on the left. An example would be census data, which should at least be close to the entire population. But if we're only sampling a population, like a poll, there is more uncertainty, and we divide by the number of samples minus 1 instead of just the number of samples. Careful attention shows that the higher n gets, the less difference there is between these numbers. So I used two actual people populations, but the population could just as well indicate the possible 10 milliliter samples you could get from a pond, or the 10 gram samples you could get from a target soil area. And hopefully it's clear that if you sampled the entire pond, you are going to get a better indicator of the average and standard deviation than if you sample just a few portions. You just don't have a pond anymore. Range is also a really common measure of spread. If you were measuring lead in drinking water, you would care about the median amount and the average amount, but it might also be valuable to see a range. So a municipal water consumer might be happy to see average and median numbers down in the 200 parts per billion, but they might also really care to see if there are outliers in the 800 parts per billion range, and if they're one of them. Seeing range numbers can be a justice issue too. There's a good chance that the top of that range is going to include some of the poorest people. So as Christians, that number really matters too. When we have larger averages, we'd expect to have larger variation as well. We can normalize the standard deviation to the mean by using relative standard deviation. Notice again, there are two forms of this, sigma over mu for population and S over x bar for sample. These are often expressed as percents rather than decimals, in which case we'd multiply by 100%. Our final measure of spread is variance, which is just standard deviation squared, again with two types depending on population versus sample. We use our measures of central tendency, mostly the mean, as a way of defining the types of error we might see in an analysis. We do this with either absolute error, that is the difference between the measured mean, x bar, and the true population mean, mu. If the measured mean is greater than the true mean, the error is positive. If it is less, the error is negative. But more often, we actually scale the error based on the true value by dividing the absolute error by the true value and reporting as a percent, the percent relative error, or just percent error. You've done this before in Gen Chem. This is the standard for indicating the accuracy of our measurements. In Lab 1, you just reported it as percent error. There are many types of determinate errors, that is, non-random errors that could occur. Because they aren't random, they affect accuracy and not precision. The first happens in sampling. If the samples aren't representative, we'll never get a true value. The second is a method error. Like if you don't tare a scale with the lid closed, it will always read incorrectly in the same direction, and so it will be inaccurate. Or if the signal from a pH meter has drifted, the readings may be systematically high or low. Measurement errors are insidious. If you have a volumetric flask that has a tolerance, the actual error in that will be in that tolerance range and always in the same magnitude and direction. So even though it says plus or minus, it will always be plus or always be minus for the same volumetric flask. If you measure with the same volumetric flask every time, you'll end up with all your errors in the same direction, even if you measure correctly. Finally, there are personal errors. This could be error from not looking directly across a graduated cylinder when you measure. Again, that's called parallax error. It could be always over titrating when the colors are used because you can't see colors as well. Like that's an error that I usually have. It could be you just aren't doing it right. Determinate errors usually have a definable source and are therefore, at least in theory, preventable. If you can't find the source of an error, you can still work to minimize it. If your error is constant, that is, your error is always the same absolute size, you can often take larger samples. Any constant error can be dwarfed by a much larger sample size because while the absolute error will stay the same, the percent error will drop. If the error does change with scale, it's considered proportional error. Generally, we control these with reference materials and calibration. For example, we occasionally check our scales against 100-gram reference standards to make sure that we're reading consistently across the entire range of a scale. For concentration methods, we might take readings of known concentrations of materials, or we might standardize a curve every time. The other types of errors are indeterminate. We can't determine what the cause is or what direction the errors will affect the reading. Because these errors are distributed randomly, they won't affect the accuracy of the experiment, but they will affect the precision. And because we don't affect the accuracy, we often don't call indeterminate error an error at all. We call it uncertainty. We talk about two types of situations that we look at indeterminate error. The first is repeatability. If you did everything the exact same way using the exact same equipment in the exact same space, you'd still get variation. That's repeatability. If you took the measurement at a different time or at a different place or with different equipment, you would get less precise measurements. We'd use that precision to indicate how reproducible it is, and it would always be less reproducible than repeatable. It might seem like that's worse, but reproducibility actually is a better measure because it takes into account some of the determinate errors within a lab, temperature variations, variations in glassware, and even minor user errors. It's hard to measure reproducibility though, because in research that means that someone else has to be trained to do what you do and then do it somewhere else. In standard methods, many labs will be performing the same analysis, and reproducibility becomes easy to measure. As we're learning, we'll be mostly defining the repeatability as you take replicate measurements and then define the standard deviation. When we take real measurements, we in chemistry will never measure the entire population. And we know that the population has a predictable distribution. Some values will be high and some will be low. The problem is, we don't really know the population standard deviation either, since we're limited by our ability to test. So instead, we estimate how far off our measured mean, indicated as x bar, is from the population mean. To do this, we use a calculation called the standard error of the mean, indicated as S subscript m. The standard error of the mean is a measure of accuracy, even though the calculation involves and looks like the standard deviation. The idea is that if you know that you're taking a limited number of samples, indicated by that big N, then you're seeing variation in the values indicated by the standard deviation S, you know that there's some random chance that all of your samples are high or all of your samples are low, just because you haven't sampled everything. So if we want to get better numbers, we really have two options. One of the options is that we can make the standard deviation lower by improving the precision, or we can increase the number of samples that we take. Note that these don't affect the standard deviation evenly. The standard error goes down more with improvements of precision than it does with increases in the number of samples. Even if you don't memorize the math here, this is useful descriptively. More precise measurements improve accuracy much greater because we have limited samples, and it takes incredible increases in sampling to overcome the poor precision. It's important to realize that absolute error, sometimes just abbreviated as error, and uncertainty are not the same. Absolute error is problematic because it actually gives you the wrong value. Uncertainty should give you a range of possibilities that should include the right value. So high uncertainty isn't as problematic. You can still know something about a sample, but the higher the uncertainty becomes, the less value the information has. When we have uncertainty in one measurement, it may be easy to define. However, many values come from multiple measurements, like density or sums. Because uncertainties happen randomly, it is unlikely that both uncertainties will be at their full magnitude in the same direction. So uncertainties in measurements are not added directly, but instead follow a scale. If you look at the second and third line, you might notice that for addition and subtraction, the uncertainty is essentially calculated like finding the hypotenuse based on those absolute uncertainties. And for multiplication, it's like finding the hypotenuse, but based on relative uncertainties instead. They're both divided by the actual scale of each value. If we have multiple functions, we'd propagate uncertainty according to the order of operations, which is what we're going to be focusing on next. In our last few slides, we talked about how real measurements will have some variation and how populations have some variation. However, the population and sample means and standard deviations generally aren't exactly the same. So our goal with our measurements is to figure out how close our value is to the actual population mean. This is a statistical problem, and statistics are great at making predictable outcomes for normal distributions. Every normal distribution will have the same percentage of values within one standard deviation, or within two standard deviations, and so on. You can see that in the bottom right. It doesn't matter what the shape of the distribution is, any of the shapes on the bottom left will be the same. We'd still have about 68% of the possible values that fall within one standard deviation, about 95% within two, and 99% within three. So we know that for any sample, there will be a 68% chance that the value will be within one standard deviation of the mean. We can choose, however, many standard deviations we want to go out from the true value, and we'll have a defined chance of the measured value falling within that range. So this equation shows that. We'd say any individual x of I, is equal to the population mean, that mu value, plus or minus some number of standard deviations times the standard deviation. We'd say that there's some confidence that they'd fit in the range. So for example, we can be 95% confident that a measured value will be within 1.96 standard deviations of the mean every time. That's great, but we still don't know what the true value is. We're still just measuring samples. When we measure normal data, we'll get a wide range of very specific values. Plotting these as a histogram, a bar graph where we plot the frequencies of values within a certain range, allows us to see that we have something that is somewhat like a normal curve, but not exactly. If we add more data, we get a more normal-looking curve. No matter how much we sample, though, we'll always have incomplete data, which means that anytime we know the mean, it's because we knew the other samples, or the mean can help us to know a missing sample. This means the data is constrained. It has fewer degrees of freedom. That's why our standard deviation calculations for samples are divided by n-1 instead of n. The n-1 indicates that data is constrained and has fewer degrees of freedom. There are always 1 degree of freedom less than the number of samples that we take. All this is really useful because we can use what we know about a sample mean to tell us about that population mean. Right? We can only take a certain number of samples, but we still have some idea of what that mu, the population mean, is. So we'd use an equation mu equals x bar plus or minus ts over the square root of n. This should look very familiar. The relationship between mu and x bar based on a certain number of standard deviations. But instead of having the number of standard deviations, we have something that looks an awful lot like the standard error of the mean that we talked about a few slides back. So here's the difference. We don't actually know the true standard deviation, the sigma. So instead, we have the sample standard deviation and then some error. The t value is how we account for the error of the standard deviation, or how we account for the uncertainty in that value. So we will use tabulated values for the uncertainty of our standard deviation, that t value, based on our degrees of freedom and some confidence interval. So in chemistry, we usually indicate a 95% confidence level. So we know we're generally going to report our values with some uncertainty. Trinity's mission states that true education involves the whole person as a thinking, feeling being. You are a thinking, feeling being. So you also know that there are some things that just don't make any sense. For example, 4.3 plus or minus 3 parts per billion doesn't make any sense because when you're reporting uncertainty in the ones digit, you really don't know that tenths digit to any degree of certainty. Instead, you should report it as 4 plus or minus 3. Or if you can't distinguish the number from 0 or negative values, there's a good chance that you're below the limit of detection, and so you should indicate that you don't actually know that carefully. So like 2 plus or minus 3 goes to -1, but you know you can't have -1. It's also worth noting that if you see things systematically increasing or decreasing, rather than randomly distributed, you have a drift in your signal and you probably need to recalibrate. You shouldn't have your numbers always going up or always going down. So the rules so far have told us how we should be reporting our data. We use the equation we talked about before to define X bar in terms of the population mean, which allows us to indicate the range the population mean would fall in under a 95% degree of certainty. But how do we know if our value is actually right? So take the 3 examples shown. It's hopefully clear that the 2 distributions shown in B are pretty much the same. And hopefully it's clear that the distributions in A are clearly different. We need to define how close our measurement needs to be to the actual distribution for us to consider an accurate measurement. So in a situation like C, we can say if it's the same or not. We start out by saying that they are measuring the same thing. We assume that they're going to look like B. We call this the null hypothesis. Again, the null hypothesis is that the data we are measuring is the same as the reference data. If the null hypothesis is true, we'd say the values are not significantly different. The alternative hypothesis is that we're measuring something different. We'd say the difference in the measurements is statistically significantly different. Because the tails of these distributions go on forever, we have to cut off somewhere. That's where the confidence value for T really matters. In chemistry, we always choose a 95% confidence level. But that means that every time we indicate that there's a difference between data, we have a 5% chance that there actually wasn't. There's also a chance that when we indicate no difference, there actually was a difference. So these tests give us a benchmark to think about difference in data, but there's actually some chance that we'd reach a completely different conclusion coming from the same starting point. When we're comparing to a population mean, we call these types of tests a t-test. And we can perform 2 different types of t-tests against the population, a one-tailed test, shown in B or C, or a two-tailed test, as shown in A. One-tailed tests assume that 5% of the possible data that we would consider significantly different would all be on one side, the left side for B or the right side for C. A two-tailed test assumes that the 5% rejected could be on either side, which means only a 2.5% would be rejected on either side. In reality, our data is either high or low in most cases, but we don't know which. In chemistry, we normally perform two-tailed tests because we don't know which side the uncertainty is on. And because the bounds are further out in a two-tailed test than a one-tailed test, this makes us less likely to reject the null hypothesis. That's another way of saying that we're more likely to accept values as being statistically similar than rejecting them as significantly different. Even though we're dealing with uncertainty, because we're ultimately dealing with an evaluation of yes, they are the same, or no, these are not the same, that will always lead to a chance of error. We can't avoid the error. If we reject a value that shouldn't be rejected, like if we had a value in one of the blue highlighted areas of a distribution, that's called type 1 error. If we increase the confidence level, we can make those blue areas smaller, but we're also reporting a much higher range. That unfortunately increases another type of error called type 2 error, where there are values that are in fact different, but we would consider them the same anyway. The more inclusively we set our definitions by increasing the confidence level to like 99% or 99.7%, the more likely we are to include values that are in fact different. So which test, a one-tailed test or a two-tailed test, is more likely to give a type 1 error? All of our t-tests are going to follow the same basic form shown here. We'll be using the actual average we have, that X bar, and the standard deviation we have, the S, along with uncertainty that comes from the t-table, and the number of samples we have to see if we are actually in the range of the material. The easiest way to do this is to solve this equation for t, given every other value. That's the minimum value of uncertainty in the standard deviation we'd need for the population to fall within range. We call this T-EXP, or the T-experimental. Once we calculate the T-experimental, we'd look up the T value from the table. We'd call this looked up value the T-critical. If the calculated uncertainty for our experiment, the T-experimental, indicated by the blue distribution, is bigger than what we should see, the T-critical, indicated by the black bar, we know the value we got from the experiment is significantly different than the known value. This is the case in B. We'd say that we have a 95% confidence level that our values are in fact different. Of course, if the value is very far out, we might be able to say that we are 99% confident the values are different, or even more. On the other hand, if the T-experimental, again in the blue distribution, is less than what we see from the table, again the black bar, we'd say that these values are not significantly different at a 95% confidence level, which you can see in the illustration for C. That is notably not the same as saying that we are 95% sure these values are the same. We assume that they are the same, and we're 95% sure that we don't need to reject them. Lower confidence intervals actually give us more certainty that our values are the same because they have a tighter window of values that we're looking at to include. If we have two sets of data, either a population mean and standard deviation, or two sample means and standard deviations, we may want to test if the standard deviations or variances between the samples are the same. This can help us to know if one analyst is less precise than another, but it can also help us to compare methods of analysis. It's actually also important for comparing certain types of data. The calculations are more complicated if the two standard deviations are not similar. To compare standard deviations or variances, we divide the larger variance by the smaller variance to calculate an experimental F value. We compare the F experimental to an F critical value from the tabulated values shown here. Notice that there are two axes in this table for the F values. Since the larger number will always be on top, we'll look for the degrees of freedom associated with the larger variance in the columns. We'll look for the degrees of freedom associated with the smaller variance in the rows. Remember that degrees of freedom is the number of samples minus 1 in most cases. So if it's a population variance, there are infinite degrees of freedom, but otherwise we would use n minus 1. If it is a population variance, just choose the highest value for degrees of freedom from the rows. There are actually three different ways we might choose to apply the t-test to compare values. The first, comparing to the population mean, mu, is the way that we've already discussed. The other two are variations on this test applied to either a sample or population that we test under different conditions, in which case we're comparing x bar and x bar under each of those conditions. We're trying to see if those two tests are the same. Alternatively, if we have collections of the exact same samples collected under two conditions, like sample A is tested under each condition, sample B is tested under each condition, etc., we'd want to compare based on the differences between the individual measurements, because we know that all readings for A should be similar and all readings for B should be similar, and so on. I'm going to walk you through how sampling from the two conditions is related to the t-test we did before. I want you to see qualitatively what is going on with this math, not memorize the math or be able to derive it. So first, we're going to start out with our t-test in its general form. Remember that our Ts over root n is essentially a measure of the standard error of the mean, applied to a particular level of confidence. But we don't just have one standard error anymore. We have two that will combine, just like our measurement uncertainties, as squares. So our overall standard error should be a combination of the two standard errors as shown here. We can solve this equation for a simplified expression, so we have just the standard error as shown. We can always use this expression for standard error instead of the s over root n in the original equation. So we'd substitute this in instead of s over root n, and we'd still multiply by t. If our standard deviations aren't very different from each other, we'd use an f-test to show that. The actual calculation is actually a little bit easier if we use a combined standard deviation, or S pooled, instead of individual values. This allows us to combine the fractions, factor out S pooled, and then define the entire system just in terms of the S pooled and the numbers of samples. Our final result is that we can compare the two means, X bar, using T times the standard error. The standard equation in this, or standard error in this equation, looks a little bit different here, but it's just a relic of propagating those 2 degrees of freedom instead of 1. That's why you have the mixed denominator. But my only point in this was to show you that this is very much an application of the same t-test. You can always look up the equation and apply the numbers. So now we know what our standard equation should look like based on the standard error of the mean. But how do we calculate that S pooled, the S subscript P? Because we have 2 samples, each with n-1 degrees of freedom, the overall degrees of freedom is n1 plus n2 minus 2. Each value has to be compared to the mean for the mode of testing and the difference squared, but we can combine all of that into what is otherwise a very normal form for standard deviation, essentially just 2 differences of means, each one squared and then divided by our total degrees of freedom. This is great, but if the deviations are not similar, we need to stick with each standard deviation separately, which gives us a t-test that looks kind of like this, which is not so bad. This seems actually simpler than the other test, except that you need to calculate the degrees of freedom for the t-table lookup using this craziness. So it's easier to use the S pooled as long as the F test allows it. Final case is a comparison between each individual sample. Like if we had multiple blood draws from different individuals and we were comparing 2 methods to test the iron in those bloods. We actually see no change in the standard error part of this equation, except that instead of using the standard deviation of the samples, we use the standard deviation of the difference, here indicated by SD. We also calculate the average difference, here D bar, instead of the averages themselves, and we assume that that average difference should lie within the confidence intervals from 0, because the difference ideally is 0. It's easy to set this up in Excel. You'd give the 2 numbers for different methods for looking at a sample, each labeled by their sample number, and you'd calculate the difference for each one, and then the mean, standard deviation, and t calculated for those differences. Sometimes, even with statistical data, you get that one data point that you know someone, let's call him Mike, measured. And it doesn't make any sense, and you're pretty sure that he screwed something up. How do you know that it's Mike and not some strangely high data point? We use a test for outliers. There are multiple ways to do this, and they're all statistically driven. The first is Dixon's Q-test. We take the smallest gap between the so-called Mike's data and divide it by the entire range to get an experimental Q value. If the experimental Q is less than the tabulated Q, we should keep the data. If the Q experimental is more than the expected Q, we should get rid of it. Other tests compare the outlier to the mean and divide by the standard deviation. This is the Grubbs test and the almost identical Chauvinet's criterion, which uses the z values that are more widely available than the standard deviation values. Both of these are more robust tests, but are rarely used. You should never end up with unreasonably high precision in your data when you do this, and you should always do this before any analysis. You can't remove your bias afterwards. So if you think something's an outlier, check it first before anything else, especially before running the t-test. Our detection limits have statistical definitions. If you take a blank multiple times, you can get a standard deviation for that blank. And we assume that we can only know something for sure if we have 3 times the standard deviation of the blank signal or greater. That's essentially saying that we know the signal didn't come from the blank at a 99.865% confidence level. That also means that there's about a 0.1% chance that any signal that we see that we're actually interpreting as a reading actually was just random. That level of detection is important because we often use detection, a qualitative measure, to say if there's a contaminant present or not. So if you had random blank signal and it actually was telling you that you had lead, even though there was no lead, you might actually be chasing down problems that aren't there. Sometimes we also talk about the limit of identification rather than detection. It adds the standard deviation of the analyte signal at that level on top of the 3 times standard deviation of blank. By using both the analyte signal and the blank signal, we can be equally sure that a non-detect at the limit of identification is actually a zero value, as we can be sure of a detection actually meaning something. If we want to not just detect, but to actually give a number of something, we generally start doing that at 10 standard deviations above the blank signal, at which point the chances that our signal is coming from the blank are astronomically small.